Okay, on to questions 3 through 6. These are some word problems that we're going to use graphical methods to solve. We may use a little bit of equation work as well. A poorly tuned car accelerates from rest to a speed of 28 meters per second in 20 seconds. So we have car, poorly tuned car, starts off at rest, V initial equals 0 meters per second, V final equals 28 meters per second. It takes a time of 20 seconds. So V initial, V final, and time is what we have. All right, so somewhere in the middle would be slower. Sketch a quantitative velocity versus time graph. So we're going 20 seconds. I think I said, oh, I'm going to be simple here. I'll just say 5, 10, 15, 20 seconds, and 10, 20, 30, 10, 20, 30, and that is meters per second. So time is in seconds, velocity is in meters per second. So it gets up to 28, so this would be 25, 28 would be maybe right there, in 20 seconds. So it starts at 0 meters per second, in 0 seconds, it's up to 28. So there's your velocity versus time graph, something like that. That's great. So determine the average acceleration of the car. Well, acceleration is the slope of this velocity versus time graph, right? So the slope equals acceleration. All right. So the slope, it's rise over run. So it's plus 30, or plus 28 meters per second in 20 seconds. You could also think of that as being the change in velocity divided by the time, right? It's going up 28 meters per second. There's your 20 meters per second in a time of 20 seconds. So that's plus 1.4 meters per second each second. All right, it could be acceleration, which is equal to change in velocity over time. So slope of the line, or simply change velocity. How far does the car travel in this time? All right, the trick with this is it wasn't a constant velocity, right? So in the past we would say, okay, distance equals velocity times time. Well, technically it's average velocity. We can't use this because it's not a constant velocity, okay? It's 30, it starts at 0, ends at 30. It's not a constant velocity. We can't simply say, 28 meters per second. We can't simply say 28 meters per second times 20 seconds because it didn't even get up to 28 meters per second until the very end of the interval. All right, so I should be writing delta x, not d here. So what we're going to use is the graph here. Turns out that the displacement of the object equals the area under the curve. Now the area under the curve is the area bounded by the line and the x-axis. So it's a triangle. And that triangle here has a base of 20 seconds and a height of 30 meters per second. So I can't use this really. So let's do this. Delta x equals 1/2 of base times height, which equals 1/2 of 20 seconds times 30 meters per second. All right. 28. I keep saying 30 because I did that once. 1/2 of 20 times 28, which is 0.5 times 20 times 28 is 280. 280 meters. It's delta x. Now, you might notice that I could cover the same amount of area if I drew a rectangle at about 14 meters per second. Turns out the average velocity here is actually, to find the average velocity, you can simply add initial, v initial, and v final together and divide by 2, turns out. Alright? So the average velocity, delta x, ends up being, okay, v final plus the initial, so it's 0 plus 30, or 0 plus 28. The average velocity was 0 plus 28 divided by 2, which is 14 meters per second, times 20 seconds. That ends up being 280 meters. Hey, look, they're the same. So you can do 1/2 base times height, or you can make a rectangle out of it and do 14 meters per second on average for 20 seconds. Pretty cool. All right. There's another one. Car has a speed of 30 meters per second, and after 6 seconds, the speed is 15 meters per second. All right. So another car. Looks like I'm drawing a Cybertruck or something. It's traveling at 30 meters per second, but then after 6 seconds, it's only traveling 15 meters per second. So the initial is 30, the final is 15, and it took a time of 6 seconds. So 1, 2, 3, 4, 5, 6 seconds. 1, 2, 3, 4, 5, 6. Units are seconds. Units here are meters per second. All right, so the velocity, meters per second, now we got to do the scale here. So 10, 20, 30, 30, 20, 10 meters per second. Started at 30, ended at 15. All right, so I'll try to draw this line nice and straight. Oh, pretty good, not bad. About like that. It says determine the car's average acceleration. So that's the slope of the line again. Rise over run, but notice the run this time goes down. You're losing velocity in this one. So acceleration is change in velocity over time. So I'm going to write change in velocity. You can also always write v final minus v initial for change in something, right? So v final is 30, v initial was 15 in 6 seconds. So A equals negative 15 meters per second in 6 seconds. So you don't have to show all this work. If you see the change is negative 15, you just go right to negative 15 over 6. So 15 over 6 is 2.5. So it's negative 2.5 meters per second each second. So the speed's going down by 2.5 meters per second each second. And nothing more to do here. If I wanted to, let's say I added a part D. All right, there is no part D, but let's say I added it. Find the displacement, delta x. Well, find the displacement here, we could do average velocity times time, or we could find the area under the curve. Right? The area under the curve here, we'd break into a triangle and a rectangle. Right? So we could either say average velocity times time, average of 30 and 15. Ooh, let's just do that. It's going to be right in the middle, right? 30 plus 15 divided by 2 is about 22.5, so it'd be an average of 22.5 meters per second for 6 seconds. That's about 135 meters. Or you could do delta x equals base times height plus 1/2 base times height. So this distance here, base times height, is 6 times 15, which would be 90 meters. All right. And then this one is base times height equals 90 meters equals delta x for that part. This part here, delta x equals 1/2 of base times height. It's the same base and the same height. 1/2 of 6 seconds times 15 meters per second. So that would be another 45 meters. So 45. You add them both together. And so you get delta x equals 135 meters. Okay? So that's kind of an interesting one. You gotta watch out. The height is from here to here. The height's not 30, right? Height's not 30, it's 15. The triangle. That was an extra part I added though, so don't get too confused by that. Alright, a bus initially moving at 20 meters per second slows by 4 meters each second. Draw a diagram of the situation. Well, the thing here is, this doesn't tell us how long to do it for. So it's going 20 meters per second. A second later, if it's slowing by 4 meters per second, it would be 16 meters per second. And then another second later, it would be 12 meters per second. And so on, right? Slowing down by 4 meters per second each second. Got your quantitative velocity versus time graph on the given axis. Oh, but it doesn't tell me how long to go, right? How much take does, okay. So it says how much time does it take the bus to stop. So let's set up a vertical scale here first. We gotta be at 20 to start off. So let's do, oh, I don't know. What should we do? If we break it into 10, 20, let's say 10, 20. All right. Seconds. Well, how long is it going to take to stop? Well, I can see it's going to go 1 second, 2 seconds, then it's going to be 3 seconds, it's going to be at 8, 4 seconds, it's going to be at 4, 5 seconds, it's going to be at 0. So it's going to take 5 seconds to stop. So let me just write that down and see if I can prove it mathematically. 1, 2, 3, 4, 5 seconds. I know it's going to go right down from 20 to that. So each second it's going to lose 4 meters per second. So it's going to take 5 seconds to stop. So let's see, how can I prove this? Well, 4 meters per second each second, that's the acceleration, that's the initial. All right. What is V final? V final is 0. Right? So when we say acceleration equals change in velocity over time, well, the acceleration is I'm slowing down, so the acceleration is actually -4 meters per second each second. Change of velocity is -20 meters per second. We're losing 20 meters per second divided by the time, t. So multiply both sides by t, right? Divide both sides by -4. We get t equals -20 meters per second divided by -4 meters per second each second. 20 over 4 is 5. Negative, negative, that means positive. T equals 5. Meter per seconds cancel. We're left with 5.0 seconds for the time. How far does the bus travel? Well, that's going to be this area right here. Delta x, or average velocity times time. So, delta x equals 1/2 base times height, which equals 1/2 of 5 seconds times the height of 20 meters per second. So that'd be 50 meters. 5 times 20 is 100. Half of 100 is 50. Or delta x equals average velocity times time. All right, the average velocity here is simply 20 plus 0 divided by 2. It's the average of the initial and final, so it's 10 meters per second on average times 5 seconds equals 50 meters. So it all works out there. Very cool. All right, number 6, physics student skis down a slope with a constant acceleration of 2.0 meters per second squared for 15 seconds. All right, draw a diagram. Okay, so we've got a slope. All right, the skier. Should give myself a little more room. All right. All right. Okay. So, it doesn't say where to start it at, but usually 0 on a ski slope, right? Second, acceleration is 2.0 meters per second squared. Time is 5.0 seconds. All right. So, sketch quantitative velocity versus time graph on the axis. Well, the problem is I don't know the final velocity. So, what we need to do is we have to figure out the final velocity, basically. We know it's going up by 2 meters per second each second. It says meters per second squared. That's the same as saying 2.0 meters per second each second. So, if we know it's going to do it for 15 seconds, it's going to go up each second by 2 meters per second, then V final is going to be acceleration times time plus V initial. All right, that we learned in the lab, but that's really just the acceleration formula as well. You could also say, okay, A equals delta V over T, multiply both sides by T, we get delta V equals acceleration times time. Same thing as this, right? Delta V, all we did was move the V initial to that side. So delta V is acceleration times time. That's going to be 2 meters per second times a time of 15 seconds. Seconds cancel. You get 30 meters per second for the final velocity. So you need that to be able to make this graph. 15 seconds. So let's see. 5, 10, 15. No, that's no good. We'll go 5, 10, 15. 5, 10, 15 seconds. V is meters per second. And it's going up by 2 meters per second each. So this would be, got to get up to 30. So 10, 20, 30. So 5 seconds would be 10 meters per second. 10 seconds would be 20 meters per second. 15 meters per second would be 30 meters per second. So there's that graph. So it's speeding up 2 meters per second each second. Determine the length of the slope. That's delta x. So, area under the curve. Right to there. Delta x equals 1/2 base times height. Equals 1/2 of base, which is 15 seconds, times height, which is 30 meters per second. Seconds cancel. So 15 times 30. 15 times 30, about half of that. It's 225 meters. Now, or you could have said delta x equals average velocity times time. So the average here, 15 and 10, it's 15 meters per second is the average, right? Because it's 30 meters per second plus 0 meters per second divided by 2 times 15 seconds. You get the same answer, 225 meters. All right? So those are those written up. There's a lot of stuff going on there. The main thing is to remember that acceleration is change of velocity over time. It's the slope of the line, and that the displacement is the area under the curve.